Hi guys, today's video is just going to review the first derivative test. We talked about this in Pre-Calculus 12B when we did our curve sketching unit last semester. In front of you right now, you will see an example of one of the questions I assigned for homework. This is question 4G, so if you want to just pause the video and you can look that over and see how I went through that. If you have any questions, you can post in the Teams group and we can talk about it further. All right, so let us get started. All right, the first derivative test. So we know from last semester that if the function f has a local maximum or minimum value at c, now c is just a constant, it's an x value we're talking about here, and c must be a critical value of the function f. This is what is known as Fermat's theorem. It goes on to say that not all critical numbers give rise to a maximum or minimum. For instance, recall that 0 is a critical number of the function y equals x cubed, but this function has no maximum or no minimum at a critical number. So remember, when we're actually doing the first derivative test, what we want to do is actually calculate the first derivative. So the derivative of y is y prime, or dy over dx, and the derivative of x cubed would be 3x squared. Again, recall from last unit to find the critical values, these x values that cause the derivative to equal 0, well, we would simply set the derivative equal to 0. Divide both sides by 3. And to solve for x, well, you'd have to take the square root of both sides. The square root of 0 is just 0. Okay, so there, 0 is a critical value of the function y equals x cubed. It says, but this is not a maximum or a minimum value. And I'll show you why a little, and I'll come back to this after a few minutes. Right? One way of solving this is suggested by the figure below. So it says if f is increasing to the left of a critical number c and decreasing to the right of c, then f has a local max. Okay? Remember, f is increasing if the derivative is positive. So you can see here's my critical value, c. I have a maximum here. I've drawn this curve in, and you can see that to the left of c, my tangent lines all have positive slopes. That means f prime x is greater than 0. It's positive. Okay? F prime c right here. If I drew a tangent line to the curve right here, well, notice the tangent line is horizontal. That means that f prime c at this x value, f prime, the derivative, is equal to 0. And if I move past c to the right of c, you'll notice that my tangent lines all have negative slopes. So f prime x is less than 0. The derivative is negative. That we know that c gives rise to a maximum because the derivative is positive to the left and negative to the right of c. The opposite is true for this critical value down here, which I labeled d. To the left of d, the tangent lines are negative. To the right of d, the tangent lines are positive. If the derivative goes from negative to positive at d, we have what we call a minimum. And that is, folks, is the first derivative test. You want to pause the screen here. That's essentially what you'll see. It says if f prime x changes from positive to negative, we have a max. If f prime x changes from negative to positive at c, then we have a minimum. And finally, if f prime x does not change at c, so that means it was positive to the left of c and positive to the right of c. Or it could be negative to the left of c and negative to the right of c. All right, so let's just go through an example. I'm going to show you example 1, which is completed. I'll pause it here, and then we'll work through example 2 together. This will just give you a couple of extra things to look at. Okay, so if you want to go through that or look at that, you can see that this curve, x cubed minus 3x plus 1, this is a cubic function. All right, it has a maximum at the point -1, 3, and it has a minimum at 1 comma negative 1. You can see on my little number line test up here, the derivative went from positive to negative. At negative 1 gives me a max. It goes from negative to positive at positive 1, which would give me a min. Okay, remember, positive derivatives or positive slope, the slope of the tangent line being positive, that means f, the function, is increasing. F would be rising. The y values would be getting bigger. And conversely, if the slope of the tangent line is negative, if you have a negative slope, that means the y values are decreasing. That means the function is decreasing. So let's take one from the top, example 2 here. All right, and I'll exit the full screen so you can see what's going on over here. So it says find the local maximum and minimum values of g at x. All right, so g at x is this fourth degree polynomial, x to the fourth minus 4x cubed minus 8x squared minus 1. It says use this information to sketch the graph of g. Now, we can make a fairly good sketch of this graph, but keep in mind it wouldn't be as detailed as what we went into pre-calculus 12b. I'm not really going to focus so much on the actual sketch as more, really what we want to drive home in this tutorial is how the first derivative test works and how we can locate our local maximums and minimums. But I'll show you what the curve looks like afterwards. Okay, so for starters, in order to do the first derivative test, you have to find the derivative of g at x. Okay, the derivative of g at x is g prime x, and this is just a simple little power rule question. The derivative of x to the fourth would be 4x cubed. The derivative of negative 4x cubed would be negative 12x squared. The derivative of negative 8x squared would be negative 16x. Keep in mind, we're bringing the exponent down in front, multiplying it by the coefficient 1, writing our base x, and then subtracting 1 from the coefficient. And don't forget, finally, the derivative of a constant would be 0. There's no need to write minus 0. From here, I am going to factor the first derivative. All right, 4x cubed minus 12x squared minus 16x. Well, I can take out a common factor of 4x. When I say take out a common factor of 4x, I'm going to divide all three of these terms by 4x. So I open my bracket. 4x cubed divided by 4x gives me x squared. Negative 12x squared divided by 4x gives me negative 3x. And finally, negative 16x divided by 4x gives me a negative 4. From here, inside the brackets, I have a simple trinomial. I am looking for two numbers that add to give negative 3 and multiply to give negative 4. Okay? Those numbers would be, well, the only options to multiply to give negative 4 would be a 1 and a 4 and a 2 and a 2. Remember, one of those would have to be a negative. In this case, since they add to give you a negative, the larger of the two factors would be a negative. So the numbers that work are a positive 1 and a negative 4. So once I get this factored, check this out, you should see that x times x, x squared, negative 4x, plus 1x, minus 4. If I group my negative 4x and my plus 1x, it would give me that negative 3. So these two factors here actually equal this. Now, from here, I would set my derivative equal to 0, and I would solve for x. I'm looking for the values of x that make this whole thing equal 0. Or if it were a rational function, the values of x that make it undefined as well. So take each factor. This is called the zero product principle. The only way to multiply these three factors together and get an answer of 0, one of these factors, the 4x, or this bracket x plus 1, or this bracket x minus 4, have to equal 0. Well, the truth is, it could be any one of those. All right, and you don't have to show this work. Divide both sides by 4, x would equal 0. Subtract 1 from both sides, x would equal negative 1. add 4 to both sides, x would equal 4. So what I have here are these three critical values. My critical values are x equals -1, 0, and +4. Now, there's a couple ways to tackle this from here. All right, some people like to do a little table. We decided to do a little number line test. Now remember, you're testing the first derivative. You want to find out if the first derivative is positive or negative. So what I do is I take my three critical values, -1, 0, and 4, and I draw them on a number line. That breaks this number line up into 4 intervals. This first interval right here goes from -infinity, that arrow pointing left means we're heading left forever or heading towards -infinity. So the interval will be from -infinity to -1. The next interval is pretty easy to see. It goes from -1 to 0. The third interval goes from 0 to 4. And the fourth interval goes from 4 to the extreme right, or positive infinity. What I have to do is I need to pick values of x on each interval, plug them into the first derivative to see whether my g prime x, whether the derivative works out to be a positive or a negative. Now, I don't care if it's a +20, +30, +782. I just want to know if it's positive or negative for that matter. Okay, so let's think of a number between -infinity and -1. -2 works fine. You could use -5, whatever you want, anything between -infinity and -1. If you plug a -2 in for x, this would become -8. This factor would become -1. This factor would become -6. I'd have a -8 times a -1 times a -6, or a negative times a negative times a negative. Three negatives multiplied together gives you a negative. Any number on that interval from -infinity up to -1 would give you a negative derivative. The derivative is going to be decreasing from -infinity. Sorry, the function is going to be decreasing from -infinity to -1 because the derivative is a negative. My next interval I want to test from -1 to 0. All right, you can pick -1/2 or anything between -1 and 0. It doesn't matter. 4 times -1/2, that's -2. -1/2 plus 1, that's +1/2. -1/2 minus 4, that's -4.5 or -9/2. This would be a negative. This would be a positive. This would be a negative. A negative times a positive times a negative. Well, two negatives make a positive times this positive gives me a positive. What that means is the function is increasing from -1 to 0. Between the x values of -1 and 0, my function would be increasing, going up. The y values would be getting bigger. Let's test from 0 to 4. All right, you could pick 1, 2, 3, anything you want between 0 and 4. Again, we plug these test values into the derivative. We're trying to see if the derivative is positive or negative. 4 times 1 gives me 4. 1 plus 1 is 2. 1 minus 4 is -3. Okay, so that would be a 4 times a 2 times a -3. 4 times 2 is 8 times -3 is -24. Again, I don't care if it's -24. I'm just concerned whether it's positive or negative. So again, positive times negative gives me a negative. And finally, from 4 to infinity, any number between 4 and infinity works. 5 is nice, the smallest one I can work with here. Smallest whole number, I should say. 4 times 5 is 20. 5 plus 1 is 6. 5 minus 4 is 1. 20 times 6 times 1 gives me 120. Again, I don't care that it's a 120. I just want to know if it's positive or negative. This would be a positive times a positive times a positive. So here's what I can understand, or here's what this number line tells me. It tells me that the function is increasing. The function g of x, this thing right here, this fourth degree polynomial, it's increasing from -1 to 0, or on -1 to 0, and from 4 to infinity. Notice how when I use my interval notation, I use round brackets here because it can't equal -1. It can't equal 0. It can't equal 4 because those are the values of x that make it 0. We want to know where it's positive or negative. So we exclude the -1, 0, and 4. And decreasing on the intervals that have negatives above them, well, that would be this one right here. Remember that interval went from -infinity up to -1. And the other interval with a negative above it would be from 0 to 4. Okay. We know the intervals of increase. We know the intervals of decrease. Remember our first derivative test. If something goes from negative to positive at a critical number, okay, what do we have at that critical number? Remember, negative derivative means the tangent lines would have negative slopes, or that your y values would be decreasing. And then they would be increasing. So think of it, watch my pen. Decreasing, increasing. What we have right here is a local min. I also have a local minimum right here at 4, at an x value of 4. The opposite is true at the x value of 0. I have a local maximum because to the left of 0, g at x would be increasing. My derivatives are positive. And to the right of 0, my derivatives are negative, or g at x is decreasing. So I'm going up and then back down. All right. In order to figure out the heights of the function at -1, 0, and 4, I simply plug these values back in to the original equation. All right. I have a minimum at x equals -1 and +4. Anytime you want to know the height at a given x value, you simply plug it back into the original equation. And when I work these out, let's see what I get. G at -1. -1 to the 4th is +1. -1 cubed is -1 times -4 is +4. -1 squared is 1. 1 times -8 is -8 minus 1. G at -1. 1 minus 1 is 0. 4 minus 8 is -4. So the point -1, comma -4 would be a minimum, a local minimum. G at 4. 4 to the power of 4 is 256. 4 cubed times another 4, that's a -256. 4 squared is 16. 16 times 8, that's 80 and 48, -128 minus 1. 256 minus 256 is 0. -128 minus 1 is -129. So the point 4 to the right, down 129, that would be a local minimum as well. And finally, I have a maximum when x equals 0. What is my y value when x equals 0? I simply plug that 0 back into the g at x formula. If anyone's wondering where this came from, this g at x formula, just have a look back up here. I just kind of took this guy and brought it down. And when I solve here, g at 0 equals 0 minus 0 cubed times 4, 0 minus 0 squared, that's 0 minus 1, -1. So the point 0, comma -1 is a maximum. Now, before I show you what this picture looks like, I want to go back to that question or that thing we said we'd come back to in the beginning. All right. I'll show you why x equals 0 is not a critical value of the function. So it is a critical value, but it's not a max or a minimum. All right, so if I put 0 on my number line, breaks the number line into two intervals from negative infinity to 0 and from 0 to infinity. I'm going to pick some test values. I'm going to plug these test values into the derivative. You're trying to see if the derivative is positive or negative. If I put a negative 1 in there and square it, I get a positive 1 times 3 gives me a positive 3. If I fill a 1 in there, 1 squared is 1 times 3, it gives me a positive 3. Check this out. No change means it's not a max or min. It follows this third rule of the first derivative test. If f prime x does not change at your critical value c, or at that critical value 0, then f has no max or no min at that. All right, the last thing I want to do is show you what the graph of this curve would look like. Okay, so really all I have here are 3 points to plot. -1, -4, 0, -1, and 4, negative 129. Plot those 3 points. There's 0, sorry, -1, -4. That point would be 0, -1. This point would be 4, negative 129. All right. Function is decreasing from negative infinity to -1. It's increasing from -1 to 0. Notice it slides up slightly here. Then it goes decreasing again from 0 to 4. And then it increases from 4 to infinity. There is my curve. All right. Now, back in pre-cal B, we would have done inflection points, and we would have ran through the whole process that we did in pre-calculus 12B. Right now, all we really want to focus on are finding maximums and minimums using the first derivative test. All right, there's the first derivative test for absolute maximums and absolute minimums. You can pause the video here. These are the questions I'd like you to do for homework. All right, have a great weekend.